Hello, everybody. Good to go ahead and start our day today and start off Unit 3. You're going to go ahead and go onto Classroom. You're going to find the Classwork tab. And I want you guys to find Unit 3 KWL. I'm always going to keep our KWLs from here on out. They're going to be digitized, and they are going to be under no unit so that you can always find them at the top of the Classwork tab. So you're going to click the Classwork tab and go ahead and click Unit 3 KWL. I have set up this KWL for each person individually, so we're going to go ahead and open it so we can see it right here. Okay, so this KWL is going to look a lot different from the one you guys were already filling in class. And part of this is because I've already filled a lot of this in for you. So we have our know section, our want section, and our learned section. You're going to fill this in today at your know section. So what I want you to do is take the next few minutes. You're going to pause this video, and I want you to type in here anything that you know about periodic trends from maybe your reading yesterday, anything you know about ions, ionic bonding, molecules, covalent bonding, and polar bonds or polarity. So you're going to go ahead and just fill in what you know. If you don't know anything, feel free to just write NA. Once you've finished that, you can go ahead and click play on the video, and we will resume with our notes. Okay, so something that you might notice is I already put our learning targets in the want section of your KWL, so that's something you're not going to have to do this time around. So today we are going to learn about periodic trends, and what we're going to be learning about is explaining and modeling the organization of the periodic table. So after today, you should not only be able to explain the organization of the periodic table, but you should also be able to model it, and you're going to have an opportunity to model it in tomorrow's lab/game that we're going to play. All right, so periodic trends. Once again, our learning target is right here. Here we've got our periodic table, and we're going to kind of dig into how this periodic table is arranged in the way that it is. Remember, we do know that our periodic table has our s, our p, and our d orbitals. So we have our s orbital, our p orbital, our d orbital, and our f orbital, which actually belongs here, that is down here. So we do know that it's organized in those manners, or organized in increasing energy level or increasing atomic number. So that is something that we do know, that our periodic table is organized by increasing atomic number. So you can go ahead and write that down. And because it's by increasing atomic number, we also know that it's ordered in increasing number of electrons and increasing number of protons. So those are two other things that we also know about our periodic table, along with the fact that we know our S, our P, our D, and our F subshell. We're going to look into a little bit more as to why these are organized the way that they are. The first thing that we're going to look into is atomic size. So this is the size of an atom. And when we look at atomic size, we're looking at this thing called atomic radius. And atomic radius is half the distance between the nuclei of two atoms of the same element. And of course, this is going to be when the atoms are joined. So right here off to the side, I've got a picture of two atoms. Our nucleus is here in the center. The atomic radius is going to be the distance, or the atomic radius is going to be half the distance between the two nuclei, or the distance from the nucleus to the outside edge of each atom. So as you can see here, this is our atomic radius that we're pointing to right there, which is also half, or the atomic radius is going to be half of the distance between the nuclei, which I just wrote down there. So thinking of atomic radius, in general, our sizes of our atoms, if we're thinking that atomic number means the number of electrons and the number of protons, it would make the most sense if atomic number was changing as we went through the periodic table. So we're going to, not atomic number, sorry, atomic size changes as we go through the periodic table. So in general, atomic size is going to increase from top to bottom. And we call this from top to bottom in a periodic table a group. So top to bottom is called a group, and that's something else that I'd like you to write down on your sheet or on your note sheet. So we're going to go ahead and we're going to just maybe denote it kind of up here off to the side. So these things going up and down are called groups. And from left to right, we call these periods. I have a very weird way to remember this, but it's definitely a way that you'll remember. Remember that a period usually is a menstruation cycle that occurs for a woman, and that occurs during a week in a month. And if you were to look at a calendar, a week flows from left to right or in a horizontal fashion. I know that's a really weird way to remember it, but it is a good way to remember that period moves left to right and groups or columns move top to bottom. All right, so atomic size is going to increase from top to bottom of a group. So from top down, or top to bottom, top down, we're going to actually see atomic size increasing. So atomic size increases from top down. It decreases from left to right or across the period. So across the period, we'll actually see atomic size decreasing. So from left to right, we see our atomic size decreasing. I'm going to go ahead and ask you a few questions just to check your understanding, and you'll answer these in the Edpuzzle. So I'm going to go ahead and move this periodic table back over here. You can look at yours on your sheet. So my question for you is, lithium have a bigger atomic radius than potassium? So which has a bigger atomic radius, lithium or potassium? So go ahead, take what we just learned from these notes to figure out if you think lithium or potassium has a greater atomic radius. Now that you've figured that out, hopefully you asked or answered potassium. Potassium should have a bigger atomic radius, mainly because it's farther down on the periodic table. And as we move farther down the periodic table, our atomic radius increases. Let's do another one just to check our understanding. What has a bigger atomic radius, sodium or silicon? Sodium or silicon? They are in the same period. They're in the same horizontal grouping. So what is bigger, sodium or silicon in terms of atomic radius? Based on our periodic table trends, we know as we move from left to right, our atomic size decreases. So hopefully you answered that sodium was bigger than silicon. Our biggest sized atom is going to be down in our lower left-hand corner, and our smallest sized atoms are going to be up in our upper right corner. So that is atomic size. Next, we're going to learn about ions. Ions are an atom or group of atoms that have a positive or negative charge. An atom or group of atoms with a positive or negative charge. That is going to be what an ion is. And just so we all are aware, ions form, and we'll learn this later this week, from the transfer of electrons, which we will cover when we go over our ions notes. So ions form from the transfer of electrons. In order, we need to understand what ions are in order to understand our next periodic trend, which is going to be our size of our ions. Or our ionization energy. So we've got ions. The next sheet of your paper should look something like this. Okay, so we've got sodium. Sodium originally has 11 electrons. Sodium likes to lose electrons, and when it loses electrons, it goes from 11 electrons to 10 electrons, and it forms a cation. We also have chlorine. Chlorine usually has 17 electrons, but chlorine likes to gain electrons. So when chlorine gains an electron, it goes from 17 to 18, and we have an anion. So cations are positive, anions are negative. We need this to help us understand what is known as ionization energy. So ionization energy is going to be the energy required to remove an electron from an atom. Okay? The energy required to remove an electron from an atom. And we have this thing called the first ionization energy. And first ionization energy is basically how much energy does it take to remove the very first electron off of an atom. So typically it decreases from top to bottom. So it decreases down a group and it increases across a period. So if we're looking at our periodic table, our ionization energy is going to increase from left to right, and it is going to decrease from top to bottom. So let's look at another example. Would the ionization energy of potassium be more or less than calcium next to it? So which has a greater ionization energy, potassium or calcium? Hopefully you answered calcium because it increases as we move left to right. Something else that we have that the periodic table helps us with is the group numbers in the S&P orbital, the 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A that I had you circle a while ago are actually important for our charges. So if it is in group 1A, the ion has a charge of +1. If it is in group 2A, it has a charge of +2. If it's in group 3A, it has a charge of +3. 4A gets a charge of +4. 5A gets a charge of -3. 6A gets a charge of -2. 7A gets a charge of -1. And 8A has no charge. Those are our noble gases. So those is not applicable. No charge for those guys. This is stuff we'll get into a little bit more later this week when we talk about ions a little bit more. So we have ionization energy as a trend, and we also have ionic size as a trend. So ionic size is going to differ depending on whether it's a cation or it's an anion. Remember, cations are our positives. So we put a little plus sign next to that. And anions are our negatives. We can put a little negative sign next to that. Cations are going to be smaller than the atoms from which they form. So we're going to go down and look at this picture. I have lithium. Lithium loses an electron. If I lose something, for example, if I lose weight, am I going to be bigger or smaller? Obviously, if we lose something, we're going to be smaller. So because they lose something and get that positive charge because they lose a negative electron, they actually become smaller. Now, anions are larger than the atoms from which they form. And let's look at this. If we look at fluorine, fluorine is going to gain an electron. Fluorine likes to gain an electron. And so when we gain something, we usually get bigger. So because it gains an electron, it actually becomes larger than the atom from which it formed. This one you don't have to write anything into the periodic table. I've already done it for you. But generally speaking, The size of our ions increase as we go down our periodic table, kind of like the size of our atoms increase as we go down our periodic table. And that's because there's going to be more electrons and more protons and neutrons. For example, if you look at hydrogen, hydrogen has one proton and one electron. That's going to be a lot smaller than something like francium, which has 87 of each. Now, our size of our cations. Notice that cations only go to 3A. And after 3A, they start calling them anions. And they kind of have a gap here. So the size of our cations is going to decrease as we move left to right. And the size of our anions is also going to decrease as we move left to right. And this has to do with the charges on these specific things and what they like to give and take, which we'll get into a lot more with our ions notes. But you should know this general trend that ions increase top to bottom or increase down a group. Cations and anions decrease across a period. If I was to ask a question, what has a larger ion size, lithium or beryllium? Hopefully you would answer lithium because it's farther left. If I asked what has a larger ion size, silicon or beryllium, Si or Ge, you should answer beryllium because it is farther down the periodic table. The last thing that we're going to talk about is electronegativity. First, we need to understand what electronegativity is. So, electronegativity is the ability of an element to attract electrons when the atom is in a compound. We'll learn more about electronegativity, go into greater detail with electronegativity when we learn about compounds and we learn about polarity, because it's going to play a great deal with that. The general trend for electronegativity is that it tends to decrease as we move from the top to the bottom, or it decreases down a group. And it tends to increase from left to right across the period. So we're going to see electronegativity energy increase as we move left to right down our periodic table, and it's going to decrease as we move from top to bottom. So if we were looking at our periodic table, what would have a higher electronegativity, chlorine or bromine? So we've got chlorine or bromine, which would have a higher electronegativity. Based off of this information that we just learned, hopefully, because it's farther down the periodic table, you would know that bromine is smaller in electronegativity and chlorine is larger. Once you finish these notes up, there is going to be a Google Form worksheet for you to complete on Classroom. Please feel free to ask me any questions in class tomorrow, and I will see you again soon.